Let us use an analogy to understand electric flux better. Consider water flowing through a rectangular open channel at uniform velocity and draining into a measuring jar. A valve, V1, is introduced to regulate the quantity of water flowing into the channel. The discharge, which is the quantity of water flowing per unit time, is given by the product of the velocity and area of cross-section of the opening of the regulating valve. To regulate the discharge, we increase the open area of the regulating valve, V1, assuming that the velocity of flow of water upstream remains constant. Let us install one more valve, V2, downstream to V1. V2 is pivoted to the bottom of the channel. Valve V2 can swing about a horizontal axis, which is perpendicular to the direction of flow of water. This completes the apparatus. Now for the experiment. Keep the area of the opening in both the valves the same. That is, the bottom line of the closing plate in the two valves should be at the same height. Measure discharge Q1 for 5 minutes by collecting the water in the measuring jar. Keep this measuring jar away from the downstream flow. Now, lower the closing plate of V1 without changing the position of the plate in V2. Measure discharge Q2 again for 5 minutes. Q2 will be less than Q1 as the area of opening in V1 has decreased due to the lowering of the plate. Then, swing V2 until the bottom line of the plate just touches the top surface of the water in the downstream. Remove valve V1. Measure discharge Q3 again for 5 minutes. You will find that Q3 is equal to Q2. Why is Q3 equal to Q2 when the area of opening of the two valves is different? This is because the area of opening of V2 is more than that of V1. V1 is kept perpendicular to the direction of flow of water, whereas V2 is kept at an angle to the direction of flow of water. The projected area of opening of V2 taken on a plane, which is perpendicular to the direction of flow of water, is equal to the area of opening of V1 that is kept perpendicular to the direction of flow of water. What are the conclusions that we can draw from this experiment? Q is equal to V into A, where V is the velocity of water flow and A is the area through which water flows. In this equation, A should be perpendicular to the direction of flow of water. In the event A is not perpendicular to the direction of flow of water, we should take the projected area on a plane perpendicular to the direction of flow of water. Then, the equation will be modified to Q is equal to V into A cos theta, where theta is the angle that the outward normal to the plane makes with the direction of flow of water. Here, V and A are vectors, and as Q represents the quantity of water, it is a scalar. Mathematically, we can write the equation as Q is equal to the dot product of V and A. Electric flux, phi, is analogous to Q of water. Like Q, phi is also a scalar quantity. However, unlike in Q, where there is flow of water, nothing flows in electric flux. There are only imaginary electric lines of force that cut across the area. Uniform electric field E is analogous to the velocity of water v. Mathematically, we can write the equation as phi is equal to the dot product of E and A. We can now extend this equation to curved surfaces with electric field of different magnitudes and directions at different parts of a given surface. The SI unit for electric flux is Newton meter square per coulomb. This brings you to the end of this introductory module on electric flux. You will learn more about applications of electric flux in coming modules. Consider a uniform electric field of strength E along the x-axis. Consider a rectangular surface of area A placed in the uniform electric field such that its axis makes an angle theta with the direction of the field. In other words, the area vector A, which is conventionally taken along the outward normal to the surface, makes an angle theta with the direction of the electric field. The electric flux passing normal to this area is then given as phi is equal to E dot A or phi is equal to EA cos theta. Now, consider a closed surface S placed in the uniform electric field of strength E. Consider three elements X, Y, and Z on the closed surface, having areas delta A1, delta A2, and delta A3 respectively. The electric flux through the element X is phi 1 equal to E dot dA1, and since the angle between the direction of the electric field strength E and dA1 is acute, the flux phi 1 through this surface is positive. For all such elements, the flux passes from the outside to inside. That is, they have an inwardly normal flux. Since theta is equal to 90 degrees for element Y, the electric flux for Y is equal to 0. For all such elements, the flux through the surface is 0. Similarly, since theta is obtuse for element Z, the flux through the element is negative. For all such elements, the flux through the surface passes from the inside to outside. That is, they have an outwardly normal flux. From these observations, we can say that the inwardly normal flux is negative and the outwardly normal flux is positive. Let us now consider a point charge plus Q placed at the center of a sphere of radius r. Let us now look at Gauss' law, which defines the relation between the net electric flux through a closed surface and the charge enclosed by that closed surface. This law is of fundamental importance in the calculation of electric field strengths. The closed surface is referred to as the Gaussian surface. The electric field lines of the point charge plus Q are outwardly normal to the charge and hence are outwardly normal to the sphere at all points on its surface. The magnitude of the electric field E at a distance r from the point charge is equal to 1 by 4 pi epsilon naught Q by r square. Let this be equation 1. So we see that for all points on the sphere of radius r, the magnitude of the electric field strength is the same, and it is directed away from the charge plus Q in an outwardly normal direction at each point. Therefore, we see that at each surface point, the electric field strength E is parallel to the area vector dA, which represents the area of an infinitesimally small element on the surface. Since E is parallel to vector dA, the electric flux d phi passing through this local element is equal to E dot dA is equal to E dA cos 0, and as cos 0 is equal to 1, d phi is equal to E dA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface, we now integrate d phi. Therefore, phi is equal to integral d phi, and this is equal to integral E dA. The total electric flux can also be referred to as the net electric flux. Since E is constant in magnitude for all points on the Gaussian surface, we have integral E dA is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Now, phi is equal to EA. We know that for a spherical surface, which is the Gaussian surface in the present discussion, A is equal to 4 pi r square. Therefore, we have phi is equal to E into 4 pi r square. Let this be equation 3. Substituting equation 1 in equation 3 and simplifying, we get the net flux phi is equal to Q by epsilon naught. Let this be equation 4. We see that the net flux phi is proportional to the charge Q enclosed by the Gaussian surface, or we can say that the net flux is proportional to the charge inside the Gaussian surface. Now consider two other closed surfaces, S2 and S3, around S1. We see that since S2 and S3 are closed surfaces, they can also be referred to as Gaussian surfaces. But it is important to note that the surfaces S2 and S3 are of arbitrary shape. We have seen that the net electric flux, phi, through S1 is equal to Q by epsilon naught. By definition, electric flux is the number of electric field lines passing normal to a given area. Here, we observe that the number of electric field lines that pass through S1 also pass through S2 and S3, normal to their surfaces. Hence, the net flux through S2 and S3 is equal to net flux through S1. That is, phi is equal to Q by epsilon naught. Here, we observe that the net electric flux phi through any closed surface is independent of the shape of the closed surface. Hence, we conclude that a Gaussian surface can be of any arbitrary shape. Thus, Gauss' law states that the electric flux through any closed surface is proportional to the enclosed electric charge. That is, phi is equal to Qin by epsilon naught, where Qin is the charge enclosed by the Gaussian surface. Let this be equation 5. Now consider a point charge Q placed outside a closed surface. Here, we see that the number of field lines entering the closed area is equal to the number of field lines leaving it. Therefore, the net electric flux through the closed surface is 0, and it is of importance to note that the Gaussian surface, which is the closed surface, was not enclosing the point charge. In other words, the net flux through a closed surface not enclosing any charge is 0. Let us consider a cube of side L placed in a uniform electric field of strength E, directed along the x-axis. As the cube is a closed area and the number of field lines entering the cube is equal to the number of field lines leaving it from any of its surfaces, the net flux through the cube is 0. Now let's prove the same. For any surface of the cube of area A, which is normal to the electric field of strength E, the electric flux phi passing through it is equal to EA. Now we see that the electric flux phi1 through phase 1 is equal to minus EA, since it has inward flux. And through phase 2 it is phi2, which is equal to plus EA, since the flux is outwardly normal to it. The flux through the phases 3, 4, 5 and 6, that is phi3, phi4, phi5 and phi6, respectively is equal to 0, since the area vector A is perpendicular to the direction of the electric field with respect to these phases. Therefore, the net electric flux through the cube is minus EA plus EA, which is again equal to 0. Now consider a system of discrete charges, say Q1, Q2, Q3, Q4, Q5, such that the charges Q1, Q2 and Q3 are inside the closed surface S, and the charges Q4 and Q5 are outside the Gaussian surface S. The resultant electric field strength E at any point will be equal to E1 plus E2 plus E3 plus E4 plus E5. The net flux of the resultant electric field strength E through the Gaussian surface is phi is equal to integral E dot dA, which is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA plus integral E4 dot dA plus integral E5 dot dA. Since charges Q4 and Q5 are outside the Gaussian surface, net flux due to these two charges is 0. Hence, the net flux on the surface is due to the three charges inside the Gaussian surface. That is, phi is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA. Therefore, phi is now equal to Q1 by epsilon naught plus Q2 by epsilon naught plus Q3 by epsilon naught. Or we can say that net flux through the Gaussian surface is equal to Q1 plus Q2 plus Q3 by epsilon naught. Let the total charge enclosed within the Gaussian surface be Qn, the subscript in referring to inside of the closed surface. Here, Qn is equal to Q1 plus Q2 plus Q3. Now the above equation for net flux can be written as phi is equal to integral E dot dA is equal to Qn by epsilon naught. Let this be equation 6. It is important to note that the electric field strength appearing in equation 6 is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. But the charge Qn appearing in the above equation is the charge within the Gaussian surface. In principle, Gauss law is used to calculate the electric field strength E due to a system of discrete charges or even a continuous charge distribution. From the above observations, we can look at some important points regarding Gauss law. Gauss law is applicable to any closed surface of any arbitrary shape. In the mathematical form of the Gauss law, we see that Qin is the sum of all the charges enclosed within the Gaussian surface, irrespective of their positions within the surface. The electric field strength appearing in the relation integral E dot dA is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. However, the charge Qin appearing in the above relation is the charge within the Gaussian surface. While choosing a Gaussian surface for a system of discrete charges, the Gaussian surface chosen should not pass through the system of the charges since the electric field is not well defined at the location of the charges, as it grows boundlessly as we move closer to the charge. However, in case of a continuous charge distribution, the Gaussian surface can be taken passing through the charge distribution. Symmetry is crucial to the application of Gauss law, since it makes the calculation of the electric field easier. Gauss law can be chosen to evaluate the electric field due to charge distributions that have spherical, cylindrical, or planar symmetry. Since Gauss law is based on the inverse square dependence on the distance contained in the Coulomb's law, any violation of the Gauss law indicates a departure from the Coulomb's law. In order to calculate the electric field due to a discrete charge distribution, we can apply the relation of the superposition principle. According to this principle, the net electric field strength E at any point in the field of the charge distribution is equal to the vectorial sum of the electric fields due to the individual charges at that point. This method of finding the net electric field at a point becomes impractical in the case of continuous charge distributions, such as a linear charge distribution, a planar charge distribution, or a volume charge distribution. In this module, we discuss about a linear charge distribution. Let us now consider an infinitely long straight wire carrying a uniformly distributed positive charge. Its linear charge density, lambda, is the charge per unit length of the wire. That is, lambda is equal to Q by L, where Q is the total charge on the conductor distributed over length L of the wire. The wire considered has an axis of symmetry. Consider a point O on the wire. Consider a radial vector from O to a point P whose magnitude is r. This radial vector is normal to the length of the wire. If we rotate the radial vector about the point O, we get a circle. Several points on the circumference of the circle obtained are equidistant from O. Hence, the electric field due to the charge on the element of the wire at O is equal in magnitude at all the points on the circumference. The direction of the field at any point on the circle is always radially outward. The fact that the electric field strength at any point is directed radially outward can be understood by considering two small elements of the wire at equal distances from O on either sides of it, as shown. Let the element at the point above O be A, and the element at the point below O be B. Then, the field at P due to the element at A, EA, acts along AP. Similarly, the electric field at P due to the element at B EB acts along BP. As the two elements A and B are equidistant from O, they are also equidistant from P. Thus, the magnitudes of the electric field strengths due to A and B at P are equal. To get the net electric field strength at P due to A and B, we resolve these electric fields into horizontal and vertical components. EA is resolved along AC and AO, which are along the horizontal and vertical directions. Similarly, the components of EB are along BD and BO, which are also along the horizontal and vertical directions. As the magnitude of EA and EB are equal and elements A and B are symmetric about O, the magnitudes of the horizontal components of the electric fields are also equal. Similarly, the magnitudes of the vertical components of the electric fields are also equal. We observe that the directions of the vertical components of EA and EB are opposite. Hence, they cancel each other. The horizontal components are parallel to the radial vector along OP. Thus, the net electric field at P due to the elements at A and B is equal to the sum of their horizontal components and acts radially outward. This is true for any such pair of elements considered on either side of the element at O. Thus, the field at any point under consideration, like P, is radially outwards. As the length of the wire is infinite, the electric field strength does not depend on the position of the point under consideration, P, along the length of the wire. Thus, the electric field due to the wire of infinite length is radial everywhere and in the plane normal to the length of the wire. It depends only on the magnitude of the radial vector r. Now let us calculate the electric field strength due to the charged wire at a point which is radially at a distance r from the wire. In order to calculate the electric field strength due to the wire, let us consider a Gaussian cylinder of radius r around the wire. Let the length of the Gaussian cylinder be L. According to Gauss' law, net flux phi through a Gaussian surface is equal to Qin by epsilon naught, where Qin is the charge enclosed within the Gaussian surface. Let this be equation 1. We know that phi is equal to integral E dot dA, where E is the electric field strength. At all points on the Gaussian cylinder, the electric field strength E is perpendicular to the curved surface of the cylinder. Since the electric field due to the charged wire points away from the positively charged wire as discussed earlier. If we calculate the net flux phi through the Gaussian surface, the net flux through the surface will be the sum of electric flux phi 1, phi 2 and phi 3 through the surfaces 1, 2 and 3 respectively, as shown. Surfaces marked 1 and 2 are the circular surfaces of the Gaussian cylinder, and the surface marked 3 is the curved surface of the cylinder. Let us now calculate the electric flux through surface 1, which is the flat surface of the cylinder. We know that the electric flux phi 1 is equal to E dot A, where E is the electric field and A is the area vector. This is equal to EA cos theta, where theta is the angle between the directions of electric field and the area vector. The electric field is perpendicular to this surface. Hence, in this case, theta is 90 degrees and cos 90 degrees is equal to 0. Hence, flux phi 1 through this surface is 0. Similarly, we see that the electric field is also perpendicular to surface 2, and hence flux phi 2 through this surface is also 0. Hence, the total electric flux phi is equal to the electric flux phi 3 through surface 3, which is the curved surface of the Gaussian cylinder. Let the surface 3 be assumed to be divided into infinitesimally small elements, each of area dA. There will be a net electric flux through this surface. Since the electric field strength E for any point on the surface is parallel to the area vector dA for the element under consideration. Since E will be parallel to the vector dA, we have electric flux d phi 3 passing through the element equal to E dot dA, which will be equal to E dA cos 0, and this will then be just equal to E dA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface 3, we now integrate d phi 3. Therefore, phi is equal to integral d phi 3, and this is equal to integral E dA. Since all points on the Gaussian surface 3 are equidistant from the charged wire, the magnitude of electric field strength E for any point on the Gaussian surface is a constant. Therefore, we can write phi is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Therefore, phi is equal to EA. The area A is equal to 2 pi RL, which is the curved surface area of the cylinder of length L and radius R. Substituting the value of A in the expression for total flux phi, we get phi equal to E into 2 pi RL. Let this be equation 3. From equations 1 and 3, we see that E 2 pi RL will be equal to Q by epsilon naught. Let this be equation 4. Here, Q is equal to the product of the linear charge density, lambda, and the length of the Gaussian cylinder, L. Substituting the value of Q in equation 4 and simplifying, we get E equal to lambda by 2 pi R epsilon naught. Let this be equation 5. Vectorially, E is expressed as lambda by 2 pi epsilon naught into n cap, where n cap is the radial unit vector in the plane normal to the wire. Vector n cap will point away from the wire if lambda is positive, and it will point towards the wire if lambda is negative. From expression 5, we see that the electric field strength E, due to an infinite long straight wire, is independent of the L value. Therefore, the field strength is constant in both magnitude and in direction, thus representing a uniform electric field. Let us consider a thin spherical shell S of radius r. Let the thin spherical shell be uniformly charged with a positive charge Q. the surface charge density, sigma, is the charge per unit area of the surface, and hence sigma is equal to Q by A, where Q is the charge on the spherical shell and A is the area of the sphere. This can be rearranged as Q is equal to sigma A or Q is equal to sigma into 4 pi r square, since the surface area A of the spherical shell is 4 pi r square. Let this be equation 1. The electric field due to the uniformly charged thin spherical shell has a spherical symmetry, that is, every point on the surface of the shell is at the same radial distance from the center of the shell. The electric field strength at any point is equal in magnitude and is directed radially outward, that is, along the radius vector joining the point to the center of the spherical shell. Now let us apply Gauss' law to derive an expression for the electric field strength at a point P1 outside the spherical shell and at a distance x from the shell. For this, let us imagine a sphere S1 of radius x around the charged thin spherical shell. Here, x is greater than r. This imaginary sphere S1 of radius x is a closed surface and it has area A1 equal to 4 pi x square. The imaginary sphere is the Gaussian surface. The electric flux d phi passing through a very small element of area dA1 of the Gaussian spherical surface S1 is equal to E dot dA1, which is equal to EdA cos theta, where theta is the angle between the directions of the electric field E and the area vector dA. Here, as E and dA1 are parallel to each other, theta is 0. Cos 0 is equal to 1. Therefore, d phi is equal to E dA1. The total electric flux phi is now equal to integral d phi, which is equal to integral E dA1. Since E is constant in magnitude for every point on the Gaussian surface S1, phi is equal to E into integral dA1. Now, integral dA1 is equal to A1, where A1 is the area of the imaginary Gaussian surface S1, which is equal to 4 pi x square. Therefore, total electric flux phi is equal to E into 4 pi x square. Let this be equation 2. We know that according to Gauss' law, the total electric flux passing through the Gaussian surface S1 must be equal to Qin by epsilon naught, where Qin is the charge inside the surface. Let this be equation 3. Here, Qin will be equal to the charge Q on the spherical shell. From equations 2 and 3, we see that E into 4 pi x square is equal to Qin by epsilon naught. Substituting Q for Qin and simplifying this expression, we get the magnitude of the electric field E is equal to 1 by 4 pi epsilon naught Q by x square. Let this be equation 4. Equation 4 gives the electric field strength due to the uniformly charged thin spherical shell at the point P1, which is at a distance x from the spherical shell. By substituting equation 1 in equation 4, we can express the electric field strength E in terms of the surface charge density, sigma, as shown in equation 5. The electric field strength E can be expressed in vector form as E is equal to 1 by 4 pi epsilon naught q by x square into x cap, where x cap is the unit vector along the radius vector and directed away from the charged spherical shell. If the charge q is greater than 0, the electric field is directed outward from the center of the shell, which implies it is positive. On the other hand, if the charge is less than 0, the electric field is directed inwards, which implies that it is negative. Thus, for any point P1, which is considered outside the uniformly charged shell, the electric field due to the shell is as if the entire charge on the shell is concentrated at its center. Now, consider another point P2 inside the charged spherical shell, which is at a distance b from the center of the shell. To calculate the electric field strength at P2, draw a Gaussian surface S2 of radius b. Since the Gaussian surface S2 does not enclose any charge, Q in is equal to 0 for the given surface. Hence, net flux phi through this surface is 0. According to Gauss law, the integral E dot dA is equal to Q in by epsilon naught. Given that the Gaussian surface S2 has a surface area of 4 pi b square, and since Q in is 0 for S2, the electric field strength for any point within the Gaussian surface is 0. Thus, for all distances d from the center of the spherical shell, which are greater than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is given by E, which is equal to 1 by 4 pi epsilon naught q by d square. For all distances d from the center of the spherical shell, which are less than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is 0.